To make RAG useful, we need search that understands meaning, not just keywords. In this module, documents become chunks. Chunks become embeddings, and a vector database retrieves the context most relevant to the model's answer. We've already covered how LLMs use context, why missing or stale context causes problems, and how RAG retrieves knowledge at runtime. Now we'll zoom in on the retrieval layer, embeddings and vector databases. Keyword search works well when the user and the document use the same terms. But language is flexible. A user might ask, "How do I reset my password?" while the best article says, "Account recovery instructions." A keyword system may miss that connection. Semantic retrieval looks for meaning, including synonyms and paraphrases. Embeddings make that possible by turning language into searchable representations, so RAG can retrieve context that is conceptually relevant. An embedding turns language into numbers a computer can compare. A query, sentence, paragraph, or document chunk becomes a vector, a point in meaning space. Texts about similar ideas land close together, even when they use different words. So reset password and recover account may be near each other, while shipping policy is far away. In RAG, both the documents and the user's question are embedded, then the closest matches are retrieved. The embedding model is not trying to answer the text or continue it. Its job is to create a compact numerical representation of meaning. Because queries, sentences, paragraphs, and chunks are mapped into the same mathematical space, they can be compared directly. The better the embedding captures meaning, the better the retrieval results. That is why embedding quality has such a direct impact on RAG performance. Once text has been embedded, retrieval becomes a nearest neighbor problem. The query vector is compared with stored chunk vectors, and the system scores which ones are closest. Cosine similarity measures direction, which is useful when meaning matters more than text length. Dot product also rewards alignment, but can reflect vector magnitude. Euclidean distance measures how far apart points are. After scoring, the system returns the top k chunks for the model to use. A vector database is the retrieval engine that makes this practical at scale. It stores document embeddings alongside the original text, IDs, and metadata. When a user asks a question, the query is embedded too. The database compares that query vector against millions of stored vectors and returns the closest matches, often using filters or hybrid keyword search. Those results become the context the LLM reads before answering. At runtime, RAG follows the same retrieval flow for each question. First, the user's words are converted into a query embedding in the same space as the indexed documents. Next, the vector database finds nearby document vectors. Those matches point back to the original text chunks. Finally, the LLM receives the user question plus the retrieved chunks, so its answer is grounded in relevant external context. Exact search compares every query with every stored vector. It is simple and returns the true nearest neighbors, but it becomes too slow when the collection grows to millions of embeddings. Approximate nearest neighbor search uses an index to focus on promising areas of the vector space. The results may be slightly less exact, but they are dramatically faster. For most RAG systems, that trade-off is worth it. Before documents are embedded, RAG usually splits them into meaningful chunks. Instead of embedding a whole manual as one large block, the system creates smaller passages around coherent ideas, such as an overview, setup steps, or troubleshooting notes. This helps retrieval match a question to the specific passage it needs. Chunk size is a trade-off. Larger chunks preserve context, while smaller chunks improve precision. A little overlap helps ideas carry across boundaries. Chunking is really a balance between precision and context. Fixed-size chunks are easy to implement, but they can cut through an idea and weaken retrieval. Structure-based chunks follow headings, sections, or paragraphs, so they often preserve meaning better. Larger chunks give the model more surrounding context, but may add noise. Smaller chunks retrieve more precisely, but may miss the explanation around a fact. The right choice depends on your documents and the questions users ask. To find neighbors quickly, the database needs more than stored embeddings. Brute force search compares the query against every vector, which works for tiny datasets but becomes slow and expensive at scale. An index reorganizes vectors into a search-friendly structure, more like library shelves than a pile of books. The trade-off is tuning. Faster search may use more memory or slightly affect recall, so configuration matters. Metadata gives each chunk useful context beyond the text itself. Instead of searching one undifferentiated pile, the system can filter by source, date, document type, owner, version, or permission level. That makes retrieval more precise and safer. A user should only see content they are allowed to access. Metadata also supports citations because the system can trace an answer back to its source. Good metadata improves both relevance and governance. All of these pieces come together as the retrieval layer. Before users ask questions, documents are cleaned, split into chunks, embedded, tagged with metadata, and stored in a vector database. At runtime, the user's query is embedded and searched against that index. Filters and ranking help choose the most relevant chunks, not just the closest vectors. Those chunks become the context sent to the LLM, so retrieval quality directly shapes generation quality. RAG depends on strong retrieval. Embeddings turn meaning into vectors, semantic search finds related content, and vector databases make that search fast at scale. Chunking and metadata influence what gets found, filtered, and trusted. Next, we'll look at how to use retrieved chunks effectively inside prompts and context windows.